All right, hello all. In this video, we're going to look at the basic Q-learning algorithm and understand a little bit about how it works. This is what we're going to focus on in our activity in class as well. So I'm going to share my screen. All right, so first I go through my notes go through some of the ideas and principles of this algorithm, and then we actually will have pseudocode that we'll talk through together. So the idea of Q-learning is that we want to build a table that will help us to predict the reward of a given action, a given state and a given action. So we're going to make a table that has this form, Q sub SA, where S is the set of states, A is the set of actions. So we'll have one row of the table for every state that the agent could find itself in, and one column for every action that the agent could take. So we have an entry for every combination of state and action. And what we'll do is initially we can make these arbitrary values. I think in my implementations, I just set them to 0 at the start, but you could set them to other things as well, just random values. But the idea is that over time, the value in each cell in the table will tell us how good that action is in that context, in the context of that state. How much reward do you expect to get? So the larger the number, the more positive reward there is, and the more smaller the number or even negative, the more it's not a situation you want to get into. So Q of SA is the expected value of taking action A in state S. That's sort of what I just said. Notice that I said here that the values in the table are not probabilities. They don't have to be in like between 0 and 1 and adding up to 1. But some of the algorithms actually like to have that as a feature. So you can take that, say, a row of the table, and you can scale the values so that they are between 0 and 1, and they add up to 1. And then you can treat them almost as if they were probabilities and use those probabilities to select a new element at random. It's a little bit like the roulette select if we do that. So softmax is what that's called. And in fact, it's a similar idea to the softmax output layers that deep learning networks often have. All right, so what we're going to do is to use a variation on the temporal difference equation. So here is the temporal difference equation that we looked at before. So remember, this was capital A is a prediction. So A sub k minus 1 is our prediction of what the next value in the sequence is going to be. V sub k is the actual value that we got. And this formula is helping us to update our prediction so that it's better the next time step. So we update the prediction based on the previous value. We have a learning rate called alpha, and then we look at the difference that is happening between the old value and the new, and that's we scale it by this alpha term. So when you look at our Q-learning formula, it is built out of this. So you can see that we're going to update the entry at S and A based on the old entry at S and A. So this is like A sub k and A sub k minus 1. We have alpha here. And then we have R, which is the actual reward we just got from being in state S and performing action A. And over here, you can see that we're subtracting our old prediction of what that reward would be. So those correspond to V sub k and A minus or A sub k minus 1. The only thing that we have extra in our formula is this intermediate, this middle term, which is based on looking ahead to the new situation we're going to find ourselves in and try to predict how positive or negative that situation might be. So this is called the discount rate or discount factor. It's gamma. And then we look at if we are in state S and we perform action A, we end up in a new state, S prime, and we're assuming that we know that new state. So we look at all the possible actions associated with that new state, and we pick the largest reward. So it's possible that we could get a pretty good reward by walking into a really terrible situation where we're going to get punished. for every action that we might take. And this term is meant to incorporate that, looking ahead a little bit and being like, oh, maybe we shouldn't have gone here. Maybe this wasn't the right move. So this is our formula. We're just going to use it as is. And I think I've talked through all these different pieces. So here is pseudocode for the main Q-learning algorithm. We're going to initialize the entries in the Q table to 0. You could make them arbitrary values, but in my code examples, we're actually doing them as 0. And we're going to keep another table. Here it's called N, or I refer to it as count. I think in my code, I refer to it as a frequency table. Essentially, we're going to keep track of how often we've been in each scenario. So every time we are in state S and we choose action A, we'll add 1 to the entry in that part of the table. And that way we know how well explored that scenario is. And so we can, the basic algorithm actually here doesn't even use that, but some of the variations do. So it's just a good thing to have. All right. We have some exploration probability, which here I'm setting to be 1 initially, and I'll talk a bit more about that later. And then we have the agent's initial state. And then we just go into a big loop. So we're going to repeat for n rounds. What that means depends on the task, but basically sequences of states and actions, we repeat n times, and then we see where things are at. The first step inside of that is to choose between exploration and exploitation. So, okay, so I've even turned off my share screen just so you can focus on me and not the text that's in my notes document. So exploration versus exploitation is a natural side effect of reinforcement learning being used a lot in online learning, which I mentioned earlier. So the agent is in place in the environment. They need to be taking actions to, and then they need to be learning from those actions. Suppose that we initialize the Q table with all zeros. And so then what, and we have a fixed way for it to choose what action to take. So we say, we're just going to, at every point, it'll look at the state it's in, it'll look across the actions, it'll pick the one that has the maximum reward. And it always picks the one with the maximum reward. Or it picks randomly if there are multiple ones that have the same reward. So if all of the entries are 0 initially, it'll pick a random move at first. Well, suppose that that random move gives it a small but positive reward. The next time it finds itself in that state, if it always chooses the action that has the highest reward, it's going to choose that action again and again and again. But suppose there's some other action it could take in that state that gives it a really big reward. If we have it fixed so that it always chooses the best option that it thinks it knows, it could very easily miss the actual optimal solutions. I think of this as like, I remember reading a story once of someone whose cat was crazy. When they came home from work, their cat would trip them up and wind around their legs and meow loudly until they opened up a can of cat food. And then the cat would always stick its head right underneath, and so that the cat food fell on its head every time that the owner was trying to put it into the bowl. And the owner was tearing their hair out. And the explanation was that's always worked. They always get food when they do that. So it's completely suboptimal from the cat's perspective, but yet they keep doing it because it's worked in the past. So that's sort of what would happen to our poor reinforcement learner if it only ever chooses the most, the thing that looks at any given moment like the best choice, especially early on in the process when it hasn't learned very much. So what we want it to do is to explore its options before, once it has learned enough, it can rely on what it has learned a little bit better. So that's the idea of exploration versus exploitation. In practice, what that means is some of the time early on, we want our agent to just randomly choose an action without paying any attention to reward. And then ideally, maybe as it learns, however we decide to measure that, whether that's just a number of time steps or some measure of how well it has learned, we want to change the balance so that it does less exploration and more exploitation. Okay, we're going to go back to the pseudocode now, and we'll take a look at it. All right, so we're choosing between exploration and exploitation. The way that we do that is fundamentally by having this exploration probability. What is the probability that we are going to explore versus exploit? We generate a random value between 0 and 1. And if it's less than the exploration probability, then we choose a random action. Yes, I'm going to go with that. And if it is over the exploration probability, then we want to exploit. And so in that case, we pick the action from the row in the table that matches our state S. We pick the action with the highest reward. So then we have a choice, like what do we set this exploration probability to? I set it to 1 here. You could set it to something else. This is going to make it it's just always going to choose random unless we change the exploration probability over time. If you wanted to have a fixed exploration probability, you could experiment and just set it to a value. Like maybe you only want it to choose randomly 30% of the time. Then you set it to 0.3, and then it will mostly be exploiting, but a little bit of exploration. So this is a feature that is a variation. You can come up with different variations on this for any particular implementation of the algorithm. All right, so having chosen an action, the next step is to do that action. So we hand the action off to the environment, and we wait until the environment tells us what state has resulted and what our reward was. So we get reward and state back. We have this alpha term. It could be a constant, and then the implementations that we're going to look at first, it will be a constant, but it doesn't have to be constant. There are some ways, some variations where you adapt this learning rate. This alpha term is called a learning rate, and you can adapt it to be larger or smaller based on how much you need to learn. So we'll look at some of those variations later. For now, just assume that alpha is constant, and we are not actually going to do this step, but this is where you would update alpha if you were going to update it. All right, and so then we have our formula, the one we talked about before. We update our entry in the table based on the old value, based on this term, which is looking at the difference between the actual reward and the predicted reward that we had in our Q table. And we have this discount term that's looking at what happens in the next time step and what turns out from that. So this S sub t plus 1, that's the new state that we got back from the from the environment. And this R sub t, that's the reward that we got back from the environment. All right, and then there's also, you could be updating your exploration probability over time or with some other function, so you would do that as part of this loop as well. And then you just keep doing this over and over and over again. We're going to play with this in our activity.